Okay, let's get started. Here we go. So we talked about springs at the end of last class. So without looking at your notes, could you write the work, the accomplished work or accumulated work to stretch a spring with stiffness K, X meters past its natural length? Okay, so the spring is sitting there at rest. We're going to stretch it an additional X meters. Its spring constant is K. And then recall the force required to stretch a spring is Kx. So without looking at your notes, can you write then what the work required to stretch it out X meters would be? So what do we need to know? Didn't like something I did. What do we need to know to write a work accumulation function? What do we need to know to write a work accumulation function? Yeah. Rate of change of work, right? And what did we say the rate of change of work was? Force, right? Force is the rate of change of work. So we got it, right? We can write it down because we know what the force to stretch the spring X meters is. And so then we're going to accumulate all those little bits of work as we're stretching. But, right, it gets harder and harder to pull the more you pull it, right? The force is changing for different lengths. So it's getting harder and harder to keep pulling. So then the accumulation of work is, we have to use our integral, right? So what will it be? Let's see. Lindsay. What's that? Times t? This is what she wants. Agree? Yep. Thumbs up, right? So that's good. We got force is our rate of change of work, and we're going to accumulate from 0 to x. So here's a new question. It takes 50 joules of work to stretch a spring 0.08 meters past its natural length. How much additional work would it take to stretch the work from 0.08 to 0.13 meters? So it takes 50 joules of work to stretch a spring from 0.08 meters past its natural length. How much additional work would it take to stretch it from 0.08 to 0.13 meters? So I'm going to start attendance, and I want you to think about this and work on this and see if you can make sense of the problem and see if you can write something down that would be moving towards a solution to this or moving towards an answer. Okay? So make sense of the problem and see if you can make progress on it. Okay? Take time to think about it, but also collaborate, right? Also collaborate. Okay. You set it equal to 50? That's a 0. Okay. This is what Lily did. What do you think? Is it correct? Is it the correct way of starting? Yeah, because this is an amount of work now. Amount of work is what? It's the accumulation of a lot of little bits of work. Each one is different, right? Each little bit of work is different because as you stretch, the force increases, right? It's harder and harder to pull it as you keep pulling. So that 50 is really the accumulation of a lot of little bits of work, right? Each little bit of work is what? Force. The rate is force times distance. A little bit of distance. So with a little bit of distance, we can assume a constant force for a little bit of distance. And so then we can accumulate all these little bits of work as force times distance to get the total work of 50. Okay, so now I want to solve for K. Do we put this in GC? Well, can GC help us solve for K? So given what we've done so far this semester, do we have the tools to solve for K, even with GC? We don't, right? It's like GC can evaluate integrals if we know what the rate function is, but here part of the rate is what we don't know. It's like locked in there, right? So this is an absolutely correct statement given the information in the problem, and it makes sense, but we're stuck. So what now? So this is a matter of an issue I brought up a day or two ago, a class or two ago. What's the issue here? We can't solve that thing for K. We can't solve and know what K is. That's because this integral is, remember? Open form, right? Open form. Its advantage is that it reflects the process. It reflects summing up lots of little bits of change. The disadvantage is you can't compute it. I mean, so in your head maybe, or you can't even do it with like a handheld calculator, right? So open form, it has the disadvantage of it's not computable, right? It's not computable. It doesn't give us answers readily. And so this is an example of how open form is, we're at a disadvantage here with open form in terms of what we want to figure out what that K is. So this is motivation for, can we write this in a closed form? If we could write this in a closed form, we could solve for K all day long. In closed form. Closed form means, just a elementary function like the ones you've been dealing with, polynomials, sine and cosine, exponential, logarithmic functions. Okay? Those are all your basic functions, and combinations of those, right, are all basic functions that give us a closed form. So if closed form would be our ticket here to getting K. So this is giving us motivation to start writing these. We've been writing these open form accumulation functions all semester. We want to start figuring out how can we, given an open form accumulation function, find an equivalent closed form. That's what we're going to start today. And just to reiterate the point one more time. So does what I'm saying make sense? Any questions on that? So I present this problem as a way of transitioning from springs to this idea of we could really use a way to get closed form versions of these accumulation functions. That we've been so reliant on GC to do the solving for us. So let's just one more time, let's look at remember the pushy ant? So here was the pushy ant's path, little f of x was the pushy ant's path. Open form or closed form? Is that an open form or closed form function? Closed, right? It's just elementary functions, x plus a cosine of a sine. So notice what happens when I graph that. Ready? Watch. Keep your eyes open. Nothing happened. Why not? Oh, I see. Get rid of that. Okay, ready? Watch. Keep your eyes open. Okay, so that's how fast it can graph closed form, because closed form is convenient for rapid results. It can get all those outputs of the function for every input like that. Okay, rapid fire results. That's what closed form is about. But here was our work function for the work that the accumulated work as the ant walked the path, pushing, right? And so as a function of x, and then that's what? That's an open form function, and the rate function. Look at the rate function. The rate function involved using the arc-like function, which was an open form. So within this work function, you've got it's an open form in itself, and then it has another layer of open form within it in the rate function. So I want to graph that, say, from 0 to 3, say. Turn this one off. Okay, now I'm going to graph the work function. And again, the work function, open form, and the rate function. Within that open form, the rate function has open form because it's based on the arc length function. Right, so even the technology, because of the open form situation, it's taking technology a long time to generate function values. Because it's using a numerical method. It's actually using a very small dt. It's actually using a very small dt and computing a finite number, although very many of them, a finite number of output values by like summing up, like we did at the beginning of the semester, right? We did that thing where we made a rate function, a step function of the rates, and we calculated bits of change, and we made a table, and we added them up to come up with it. Remember that? So that's basically what it's doing. So it took a long time there. So that just underscores the point. Open form is great for representing the process, but not great for computability. Closed form is what we want for computability. All right, so let's see how we're going to get closed form. We already have the tools. Let's just review it. So let's start with this. What's the net accumulation of a quantity given by a function f starting from x equals a? Review. Can you write down the net accumulation of a quantity? And the quantity is given by function f starting from x equals a. Hopefully we'd have 100% on this quiz. Hopefully. You know? Nope. No, this is the question we've been asking all semester. How do we express the net accumulation of a quantity given by, I mean, that's where we're going. We're just kind of ahead of, but that's not the answer to this question. Yeah, Nick.
Integral for f of a from x equals the integral from a to x of r from t.
Okay, so he wants the integral from a to x of, what's your function?
R f of t.
The rate of change of f, t dt. That's what you should have written down. Hopefully we had high success with that. Doing it all semester long, right? If the quantity is f, we need the rate function of f in order to write the open form, okay? And so now I want to write total accumulation. How would I write the total accumulation? I can use this integral to do that. What would total accumulation be? Yeah.
Did you just add f of 0?
F of a, our starting point, right? So yeah, so if I add f of a, then I get total accumulation. And total accumulation is f in the first place, right? So it's the function I was talking about in the first place. So all the accumulation up to a, and then the ongoing accumulation starting from a. And that would be our total amount of the quantity, f. Okay, so now I'm gonna take this and subtract f of a from both sides. And so now the right side is what we know is the net accumulation of the quantities starting from A. And since it's equal to this is also the net accumulation over here on the left, starting from A. It's just expressed differently. This first one is expressed as final minus initial, right? The final value of quantity minus the initial. That's one way to express net accumulation. And the right-hand side is what? It's the sum of many bits of change, or the accumulation of many small bits of change. So this is review, but from the total accumulation function, I can get another way to express net accumulation as final minus initial, f of x minus f of a. So if I change it around, I'm just going to change the order. That should look familiar. That's the fundamental theorem of calculus, right? That's the fundamental theorem of calculus. So the fundamental theorem of calculus is going to be our key to taking open form accumulation functions and doing what? This final minus initial way of writing the net accumulation is going to be our key to closed form. Using the fundamental theorem will be our key to getting closed form accumulation functions. So what do we need to do that? So if we had this open form accumulation function, we know what a is, we know what x is. So all that's left is, what is the function f? What is the function f? So how are we going to retrieve f or come up with f from what we have in the open form? How does it relate? So how does the function f relate to what we have if we had open form? Where's that going to come from? What do you think? Andrew, what do you think? So what about this is going to give us some clue as to what this quantity function is? These? Okay, yeah, so those are going to give us, this is going to give us where we start and end, but particularly what the value, or the function f itself. How does it relate to this? What in this is going to give us a clue to what the function f is? Yeah. Okay, but what in this, my question is, what in this integral it relates to help us get f? The rate of change function, right? The rate of change function. Yeah. So the rate of change function. And so how does the rate of change function relate to f? Like, how would you get the rate of change function if you knew f? Derivative, right? Derivative. But we have the rate and we want f. No, we've been integrating all semester. We've been integrating all semester. But what we haven't done is, given the rate function, determine what f is. So if the rate is the derivative of f, so this is now we're ready. So then what is f relative to the rate? Antiderivative, right? Antiderivative. So how do we get the function f from r sub f? Okay, that's going to be antiderivative because r sub f is the derivative of f. Right? R sub f is the derivative of f. So if we start with that, then we're doing what's called antiderivative. Okay? It's not mad at derivatives. It's not against it. Okay? It's just what's what we call going backwards from derivative. Okay? So let's see how this works. So we've got this closed form accumulation function. A to x, the rate equals f of x minus f of a. We know those are both expressing net accumulation. And so for each expression, I want you to explain the meaning of the expression. This is review from what we've been doing all semester. Then part B, you're going to use the fundamental theorem to come up with this expression, right? So you're thinking, okay, what function, if I took the derivative of it, would give me the rate function that I'm given, right? What function, if I was to take the derivative of it, would give me that rate function? All right, and then you're going to set up f of x minus f of a, and then simplify that or solve it, whatever's appropriate. Okay, so here's the ones I want you to do. So what are we thinking? So I'm trying to write this as, I want to write this as f of x minus f of a, whatever that is for this particular accumulation function. So what do I have to know? I have to know what f is, and I have to know what a is. So I'm thinking to myself, okay, I need some function that if I took the derivative of it, I would have what? Cosine, right? So I'm thinking, what function, if I took the derivative, I took its rate of change, would I get cosine? Well, that's the function f that I want. And I'm going to set it up as that function evaluated at x, and that function evaluated at whatever a is. And that will give me the closed form version of this net accumulation function. But don't skip part A. So I want you to make sure you explain A, which is explain the given expression, then use the fundamental theorem to do parts B and C. All right, see how far you make it, okay? You're either making progress or you're getting help. Oh, he's here.
And you could try to simplify it.
Okay, let's see how you're doing. First expression. Want to, let's see, interpret that expression. How about Kyle back there? Did you get it? First one. So I want to interpret the meaning of that, like we've been doing all semester. Okay, so are we accumulating bits of cosine? What are we accumulating? We're not accumulating cosine because that's the rate. We're never accumulating the rate. I know this is a common thing that students fall into. We are never accumulating rate of change. That's not what we're doing. We're accumulating the quantity, right? And we're using the rate of change to calculate bits of the quantity. But we're never accumulating the rate. So we're accumulating some quantity, right, whose rate is cosine. And it's the du. When you multiply by du, you get a little bit of the quantity, right? dy equals m dx. That's what this is. dy equals m dx. And we're accumulating dy's, little bits of the quantity, okay? So let's start from the beginning. Jessica, so can Can you interpret that whole thing? What is the meaning of that expression?
So it's the accumulation from -1/2 x.
Yep. Good. So it's the accumulation of some quantity whose rate is cosine as we go from -1/2 to x. All right, so now we want to rewrite this in closed form using the fundamental theorem. How did that go? Jeremy, did you get that? Sorry, tell me your name again. Justin. Got the J right.
Yes.
So tell me.
So fx minus fa should be
Sine of x. So sine of x minus sine of, because what? If we took the derivative of sine, we would get cosine. That's what we want. We want the function whose derivative is cosine. So it's going to be all these derivative rules you learn on the mastery test and in Calc 1, but now you have to be so good at them that you can do them backwards in your head, right? So you have to predict. It's like you're looking at the answer to the mastery test, and you have to figure out what was the original question in the mastery test. So given an answer of cosine, meaning cosine's the derivative, what is the function? Sine x. And then we want sine x minus sine of -1/2. So what's the meaning of this expression? What's the meaning of that expression? Sine x minus sine of -1/2. What's that?
Net accumulation
Of?
like 1/2 x.
It's the net accumulation of the quantity going from -1/2 to x, whose rate is cosine of x. It's the exact same thing. It has the exact same meaning and value as that. But the difference is, the only difference is what? Now we have a closed form, and now we can we can actually compute values of accumulation quickly, right? Whereas this one, we need a GC to do it. So it has the exact same meaning. This has the exact same meaning as what we said in part A for this one. The difference is closed form, computable, right? Easily computable. All right, next one. So what's the meaning of this expression? Sebastian. What? Well said. Accumulation of some function from 0 to x whose rate is 3e to the w. Okay, and did you get that in closed form? Can you tell me closed form? Say it again. Okay, so now we've got e, so we have 3e to the x is like our rate function. So we're saying, what function has that as its derivative? So this isn't x to a power. I think maybe that's what you were thinking. This is e to the x. So what function has 3e to the x as its derivative? Remember? What's that? Just e to the x? 3e to the x, right? Yeah, I thought you just said e to the x. Right? So this is the special function where it's its own derivative, right? So if that function, the derivative of it is the same as the original function. So 3e to the x, is that all? Is that our closed form? Minus 3e to the 0, which is the same as? E to the 0 is 1. So voila, we've got closed form now. Closed form, so we knew what this accumulation function was, but we needed GC to evaluate it. Now we don't need GC to evaluate it anymore. We could use a handheld, or if it's easy, if it's something, we can do it in our head if it's an easy X. Okay, next one. What's the meaning of this expression? Daniel.
It's the accumulation of quantities with the rate of change
x to the fourth. Yep. Accumulation of a quantity whose rate is x to the fourth, accumulating from 1 to x. And then how about antiderivative to get the enclosed form? It's the antiderivative of x to the fourth. Okay, so if we took the derivative, we'd have the lower exponent, right? So you got the right idea, but right, so we want, thinking about, if you take the derivative of a power, it goes down 1, so antiderivative means it's going to go up 1. But is x to the fifth, is its derivative x to the fourth? We need a 1/5 in there too, right? Because we know the derivative of x to the fifth would be 5x to the fourth. We only have x to the fourth. We don't have the 5. So we need a 1/5. Did you catch it? Minus 1/5. 1 to the fifth, right? Which is 1/5. So 1/5 x to the fifth minus 1/5. Closed form. Closed form net accumulation. It's the net accumulation of a quantity from 1 to x when the rate of change is x to the fourth. But now it's in closed form. Anyone get this one? So this is harder now. Kenny got it. Tell me.
All right, I got 2/3 times the quantity x squared plus 3 to the power of 3x. And then we have to add 2/3 times quantity 0 squared plus 3.
Add?
Or, oh, sorry, subtract.
Subtract. So we're going to subtract the f of a part. But let's just talk about this. So how can you check to see if this is right?
Use the chain rule.
Yeah, use the chain rule to take the derivative. And when you do that, you should get exactly the rate function that you started with, just with a's instead of x's. Right? So, and this is going to be a big theme, because when we get to these harder antiderivatives, sometimes you're just going to like take a stab at it. Do your best, right? And then what can you do? Check it by taking the derivative, because the whole point was we were trying to think of what function had this as its derivative. So we can just check that. So we can use the chain rule to check this. 3/2 times 2/3 is 1. X squared plus 3 to the 1/2. And then by the chain rule, times. Remember your mastery test? So now that's the derivative of this attempt. Does that exactly equal this? Yeah, this goes away. We got 2 times our independent, and x squared plus 3 to the 1/2. That's exactly what this is. So the question is, could you come up with that? That's the hard part. Could you come up with that or something close enough that if you checked it, you could get it? And that's where we're going. We'll work on that next time in class. All right, so then minus 2/3.
2/3 0 squared plus 3 times that quantity.
10 squared. That's a 10, not a 0. Yeah. Okay, so
Oh, yes, you got 3.
am I missing something? Oh, the 3/2. Thank you. Okay, so you had to recognize that this was the result of a chain. When you look at this and say, what's that the derivative of? Well, you have to see that that's chain rule, because this 2a was the second part, the chaining on of the derivative of a squared. Right? So you have to recognize that this is a chain rule derivative, and you're going to collapse it back together. What function, if you applied the chain rule to it, would give you that? So that's trickier, but we'll practice those. We're going to practice lots of those. Questions? Anybody have a question? Okay, so here, going back to the beginning of the class, check out this one. Integral from 0 to 0.8 kx dx. Does it look familiar? Okay, write it in, and we said that was equal to what? 50. That was the work to stretch the spring from 0 to 0.08 was 50. So now we have the tool to write that in if we can write that in closed form, then we can solve for k and we can answer that question. So can you write that in closed form? Now it's not a function, right? So it's just a value now, but it's the same thing applies as before. The fundamental theorem still applies even though that's just a value and not a function. So what were we asking? What function has kx? K is a constant, right? Kx as its derivative. What function has kx as its derivative? Any idea? Volunteer? If you took the derivative of what function would you get kx? Zipping. Yeah. What's that?
1/2 kx squared.
He wants 1/2 kx squared.
Yeah.
If you took the derivative of 1/2 kx squared, would you get kx? Some people are saying yes. Some people are. So how would you know? So the k just comes along for the right. Constants that are multiplied with derivatives and antiderivatives just hang around. So there's that. Okay. So we just hold on to it. If it's multiplied, right? If it's a constant multiple, those just hang around, right? But what about the x? So now it's the what function would give us a derivative of x? Well, that's x to the first. So we know we got to raise the power, not lower the power. So we're going to raise it to the second power. But if we just had kx squared, that derivative would be 2kx. Well, we don't have 2kx, right? So we also need the 1/2 to make the 2 go away when we take the derivative. So we're going to raise the power 1. Now we're in antiderivative. We raise the power 1. And then we need to clean up the mess. We need whatever factor we're going to need so we have the same coefficient if we took the derivative. So 2 times 1/2 goes away. K times x to the first, that's exactly what we have. All right, so now using the fundamental theorem, what does this equal? We've got our 1/2 kx squared is our f function, our quantity function. So now I want to apply the fundamental theorem. What do I get? Trinity.
1/2 k times
So that's a closed form of this. So this is a number, but it's still an open form expression of that number, right? Now we got a closed form expression for that number. Computable, right? Computable. And does it allow us to solve for k if we set it equal to 50? Easy, right? Easy. So this is 0. This goes away. So we're going to solve for k and multiply both sides by 2. Divide by 0.08 squared. So k equals 50 times 2 divided by 0.08 quantity squared. Can't do it in your head, but you can do it on a handheld really fast, right? Anyone got it? What is that? 115,000. And that's newtons per meter. Yes, do you have a question? Kenny, did you have a question?
No, that's
Okay. And so then we could keep going because it said, now what's the additional work to stretch it? An additional, what did it say? Anyone wrote it down? Okay. What was it? to 1.3? 0.13. So now we're looking for the integral from 0.08 to 0.13, and we know the spring constant. Or t dt, it doesn't matter. I can use x here because I don't have an x up here, right? Since I've got just values, I can use any symbol I want. So the work to stretch it an additional 0.05 would be from 0.08 to 0.13. And we can do it again. So now we know how to solve this, because we can get, this is a derivative, we can find what f is, plug in 0.13, plug in 0.08, and subtract, and that'll give us the work for the additional stretching from 0.08 to 0.13. Okay, so going back to this was this harder one. This is what we're going to be calling undoing the chain rule, because this was a chain rule derivative. So now we're doing antiderivatives, so we're undoing it, right? We're undoing the chain rule. And so to be good at undoing the chain rule means being really good at the chain rule. So knowing the chain rule so well that you can do it backwards. That's what we want our goal. We know and understand and can do the chain rule so well that we can now do it backwards. So let's just practice chain rule. Let's just practice some chain rule problems. Derivatives. So these are just like mastery test problems, right? Mastery test problems. Given the function, what's the rate of change function? What's the derivative? So see if you can do these in 2 minutes, and I'll trail you with the answer. Okay, you can check what you did. Hopefully you could do them that fast. So, but what we're going to do next, starting on Monday, is given rate functions like these, right? So these are rate functions, right? Given rate functions like these, could you recover the function that it came from when you took the derivative, right? So given rate functions that look like these, can you recover the original function? That's our next endeavor.